In Chapter 9, Part 2, Molecular Polarity, we want to start to ask ourselves, does the structure or the 3D orientation of a molecule determine its polarity? So, does the arrangement of a bond within a molecule determine the polarity of a molecule? For example, if we think about HCl, we know that the HCl bond is polar in this direction. Therefore, this entire molecule is polar. But if we think about CO2, so we know that CO2 looks like this in 3D space, so it is a linear molecule. We also know that the CO bond is polar in this direction. So when we look at this molecule with two CO bonds that look like this, it turns out that CO2 is nonpolar. Because the orientation of these, they exactly cancel each other out. Now, if in another course you've thought about vector math, which we are not going to do, but vectors, or we can think about it like tug of war, if the two abilities to tug, both in this direction or in this direction, are equal and opposite, they will cancel each other out. If they are unequal or all in one direction, that molecule will be overall polar. So the answer to this question is a resounding yup. So the arrangement of the bonds determines the polarity. So let's look at water, where they're all polar. So we have H2O. If we were to think about the valence electrons, it will be 2 times 1 plus 6. That gives us 8. Our Lewis dot structure would look like this. And so when we create a VSEPR structure, we know that it has a steric number of 1, 2, 3, 4. So we know that the overall orientation, hold on, I'm going to move that oxygen a little bit further to give us more space. We know that overall it is going to look like this. So we have a steric number of 4, 2 hydrogens, 2 lone pairs. So I'm going to put the hydrogens here, and we have lone pairs here. So when we think about this molecule, we know, that the OH bond is polar, with the electron density being pushed towards the oxygen. When we look at our Lewis dot structure, it falsely implies that that molecule is nonpolar. However, when we look at the VSEPR structure, the OH bonds both point towards the oxygen. And so overall, if we think about the whole molecule having a dipole moment, the overall molecule has a dipole moment in this direction. So the overall dipole is in that direction, to where the two bonds together push the electron density towards the lone pairs to give an overall dipole. Now, in a small molecule, you can basically add them up, or you can kind of look at them in comparison. So in some graphics you'll see in the book, it draws them as kind of lumpy shapes. I will mostly draw a VSEPR structure and then an arrow that says this is the direction. So let's look at a couple of examples. If we look at HCl, which we did on the first slide, we know that we have an HCl and our dipole moment looks like this. And so the answer is yes, it is polar. So now let's look at CCl4. So we're going to start with our valence electrons is 4 plus 4 times 7. And so we have our carbon in the center connected to 4 chlorines. And so we can see that this is our Lewis dot structure, which gives us a steric number of 4. So we know that the chlorine is not our central atom. Sorry about that. Just erase all of that and try again. So we know that our carbon is in the center. It is a steric number of 4, which gives us a base geometry of tetrahedral. And then all of our chlorines will be on the end. Don't forget, draw your lone pairs and any wedges and dashes. So now we have this molecule. So we know that the carbon-chlorine bond is a polar bond, but the orientation of all of these are equivalent. And so not polar. So it is a polar molecule or a nonpolar molecule composed of polar bonds. You can think about this like tug of war. None of these chlorines are any stronger than anyone else, so they can't pull the electron density to make it uneven. So a polar molecule means that the electron density is shifted unequivalently. So let's look at NH3. The valence electrons is 5 plus 3 times 1. So we have a nitrogen connected to 3 hydrogens and a lone pair. So it also has a steric number of 4. And so we're going to have our nitrogen in the center with our structures like this. So you could have put the lone pair on any of these. I tend to like to put mine on top, but you could put it anywhere. So we also know that the nitrogen-hydrogen bonds are polar in this direction. And so in this case, the molecule has 3 polar bonds all pointing in one direction. So we're going to get a polar molecule. They all push in the same direction. So they all push the electron density towards the nitrogen. And when it does that, it pushes all of it towards the lone pair. So now we have a polar molecule. So if we look at our next 2 examples of BF3 and carbon H3 chlorine, let's think about these. So in CH3Cl, our valence electrons is 4 plus 3 times 1 plus 7. So our Lewis dot structure is going to look like this. And so we can again know that our steric number is 4 with a base tetrahedral geometry. So we're going to add our hydrogens, we're going to add our chlorine. So we know that the carbon-hydrogen bonds are nonpolar. So carbon, hydrogen, nonpolar. But we know that the carbon-chlorine bond is quite polar. So this single bond is going to create a larger overall polar molecule. And so in this case, because we only have 1 chlorine and 3 hydrogens, it's polar. While when we looked at carbon tetrachloride, it was nonpolar because all of the chlorines were being pulled in the same direction. So polarity matters about the geometry overall. So our last example, which I will just rewrite down here for a little clarity of space, our valence electrons is 3 plus 3 times 7. So we're going to put our boron in the center. We have our fluorines. We're going to use up all of our valence electrons. And so if we remember, boron is one of the exceptions. And so we're okay with just 3 things being connected because it still has a formal charge of 0. So it has a steric number of 3. So boron goes in the center. At 120 degrees apart, we're going to put in our fluorines. So our structure looks like this. And now if we look at the boron-fluorine bond, it is exceptionally polar. It is a very strong polar bond. But if we draw all of our polar bonds on here, they all pull strongly out to the fluorine, but they're all equivalent. So if any one of these was something else, we would get a polar molecule. But it is nonpolar. So you can think about this. I like to picture in my mind, basically, if we were to redraw this molecule with a circle in the center, So we have a ring in the center and we have people on the ends. It's kind of like a tug of war. And each of these people is pulling the bond or pulling the electron density towards themselves. These three people are the exact same strength, so the center ring doesn't move. However, if one of the people is much, much stronger than the others, this ring will move in this direction. So the polarity of a molecule is based on the orientation or the redistribution of the electron density.